This is a documented reconstruction of real historical events, built from verified records, scientific data, and historical accounts. To understand what happened, we must first understand how it unfolded. What follows is history reconstructed. That day, a chain of natural forces, a design vulnerability, and a nuclear facility operating under extreme conditions would lead to one of the most severe nuclear accidents in modern history. It began quietly, a normal operating day at the Fukushima Daiichi nuclear power plant. The reactors were running when a massive offshore earthquake struck the region. In response, automatic shutdown systems were activated. Reactor units were brought offline as designed. On paper, the situation was under control. Inside the control rooms, indicator systems showed initial stability. But what followed was not part of the design scenario. A powerful tsunami, generated by the earthquake, struck the coastline minutes later. Water levels rose rapidly. Critical backup systems began to fail. Emergency generators were flooded. Power supply was lost. As operators assessed the situation, multiple systems were already degrading. Cooling systems required continuous electrical support, but that support was disappearing. Temperatures inside the reactor cores began to rise, slowly at first, then progressively faster. Control systems attempted to compensate, but the plant had entered a condition known as total station blackout, a state where almost all active cooling capability is lost. At that point, decay heat became the dominant force inside the reactors, and it was increasing. Operators worked under extreme uncertainty. Indicators became limited. Communication lines were unstable. But one fact was becoming clear. The reactors were no longer fully controllable through normal systems. Hydrogen gas began to accumulate inside containment structures. Pressure levels rose, and containment integrity began to weaken. Then, explosions occurred, first in Reactor 1, then Reactor 3. Structural damage spread rapidly. The situation escalated beyond initial expectations. The plant was now in a multi-unit nuclear emergency. Firefighting and cooling efforts continued under rapidly deteriorating conditions, but the core problem remained unchanged. The reactors were still heating. Outside the facility, the surrounding region remained unaware of the full scale of the crisis. What had begun as a natural disaster had evolved into a complex technological failure, and like Chernobyl, the true extent of the event was still unfolding. In the moments after the tsunami, Fukushima Daiichi entered a condition that would define the entire trajectory of the disaster, a total loss of electrical power, known as station blackout. Every active cooling system dependent on electricity was now disabled. Inside the control rooms, instruments began to fail, readings became incomplete, systems became unresponsive. Operators were now working in partial blindness, no full visibility of reactor conditions, no reliable confirmation of core status, only fragments of data and rising uncertainty. Emergency batteries activated automatically, but their capacity was limited. Minutes turned into hours, and every passing moment reduced the margin for control. Without active cooling, decay heat inside the reactor cores continued to accumulate. This heat does not stop, even when the reactor is shut down, even when the chain reaction is halted. It continues, silently, relentlessly. Temperatures inside the units began to rise beyond safe thresholds. Fuel assemblies were no longer fully submerged in coolant. This condition accelerated internal damage. Hydrogen gas began forming as zirconium cladding reacted with steam, a hidden but critical process unfolding inside sealed structures. Operators attempted external cooling measures, but access was limited. Infrastructure damage from the tsunami restricted response capabilities. Critical systems were offline or unreachable. At this stage, the situation was no longer about preventing damage, it was about slowing inevitability. Inside the containment structures, pressure continued to build. Unknown to the outside world, the reactors were entering a highly unstable state. And still, there was no clear confirmation of what was happening at the core, only indicators of worsening conditions and a system gradually moving beyond engineered limits. Inside Fukushima Daiichi, the situation continued to deteriorate. Without active cooling, the reactor cores were now driven by decay heat alone, a force invisible but constant. Temperatures continued to rise, slowly at first, then accelerating. Fuel assemblies inside the reactors began to overheat. Cladding materials started to weaken. And then, a critical chemical reaction began. Zirconium reacting with steam, producing hydrogen gas, a silent buildup inside sealed containment structures. Operators could not directly observe the core conditions, only indirect indicators were available: pressure readings, temperature estimates, incomplete system feedback. The situation was becoming increasingly uncertain. Cooling attempts continued, but every system depended on infrastructure already damaged by the tsunami. Pumps were offline, cooling loops were unstable, electrical recovery efforts were delayed. Inside the reactor vessels, water levels continued to drop. Fuel rods began to emerge from coolant coverage. This exposed them directly to extreme heat and accelerated structural degradation. Hydrogen concentration increased further, accumulating without visible warning inside a closed system with limited venting capability. At this stage, the situation was no longer a standard failure scenario. It was becoming a progressive core damage event, one that could no longer be reversed through normal operational control. And still, the full extent of the internal conditions remained unknown. The system was operating beyond observation and beyond certainty. By now, conditions inside Fukushima Daiichi had reached a critical threshold. Hydrogen gas continued to accumulate inside multiple reactor buildings, invisible, highly volatile, and trapped within confined structures. Pressure levels were rising, and containment systems were under increasing stress. Then, the first structural failure occurred, an explosion inside Reactor Unit 1, a sudden release of energy that tore through the upper structure of the building. Steel, concrete, and external panels were violently displaced. Operators and response teams initially struggled to confirm what had happened. Visual information was limited, communication was fragmented, and the full scope of the explosion was not immediately understood. But the situation did not stabilize. Hydrogen production continued and pressure conditions remained unresolved. Shortly after, a second explosion occurred, this time at Reactor Unit 3. The impact was more severe. Structural damage spread rapidly through the facility. Multiple units were now affected. and the plant had entered a multi-reactor emergency state. Emergency response teams continued their efforts, but conditions were rapidly deteriorating. Access routes were limited, equipment was failing, and radiation levels were becoming increasingly difficult to manage. At this stage, the event was no longer isolated to a single reactor. It had become a cascading structural failure across the site. Outside the facility, official communications began to escalate, but information remained incomplete, and the full severity of the situation was still not publicly understood. The disaster was now visible, but far from contained. As the explosions unfolded at Fukushima Daiichi, attention quickly shifted beyond the facility itself, to the surrounding population and to the unfolding evacuation process. Authorities began issuing evacuation orders, first for areas closest to the plant, then expanded outward as conditions worsened. Residents were instructed to leave their homes quickly and with limited information about the true scale of the incident. Roads became congested, movement slowed, and uncertainty spread through the region. Inside communication channels, information remained fragmented. Different reports described different levels of severity. There was no single clear picture of the event. Meanwhile, the plant itself continued to struggle with internal damage, but outside the facility, the crisis had already extended into civilian life. Entire communities were being relocated, families were separated during evacuation, and many residents were forced to leave without knowing when or if they would return. Public messaging remained cautious. Statements were updated gradually as new information became available, but the gap between official communication and real-time conditions continued to widen. Emergency zones were redefined repeatedly as radiation monitoring data changed and as the situation at the plant evolved. The uncertainty itself became part of the disaster. For those living near Fukushima Daiichi, the event was no longer just a technical failure. It had become a disruption of normal life, instant and irreversible in its immediate impact. And still, the full extent of the plant damage remained unclear to the outside world. In the days and weeks that followed, Fukushima Daiichi became the center of an unprecedented nuclear emergency response. Containment efforts continued, cooling operations were gradually restored, and stabilization of the reactors became the primary objective. But the damage had already been done. The event had moved beyond immediate control and into long-term consequence. Large areas surrounding the plant were designated as evacuation zones. Some regions remained restricted for extended periods, and in certain areas, human return would not happen for years. Environmental monitoring continued across land, water, and air as scientists assessed the spread and behavior of radioactive materials. The accident triggered a global reassessment of nuclear safety standards. Reactor design protocols were reviewed. Emergency preparedness systems were re-evaluated, and operational assumptions were questioned at an international level. Fukushima Daiichi remained structurally damaged and partially decommissioned over time, its internal condition requiring long-term containment strategies extending across decades. For Japan, the event became a defining modern disaster, not only in engineering terms, but in public memory. And in the broader history of nuclear energy, Fukushima stood as a reminder that even advanced systems can be pushed beyond their designed limits. What remained was not only a damaged facility, but a long-term process of recovery, monitoring, and containment, still ongoing, even years later. And as with all major nuclear events, the full legacy of Fukushima Daiichi would continue to unfold over time. What remains is no longer the event itself, but its consequence, a record shaped by loss, containment, and time. The world moved forward, but it did not forget, and neither should we, because understanding what happened is how we prevent it from repeating.